In the previous videos, you guys learnt about Einstein's equation, correct? And also you learnt about what is nuclear mass, density and all those things. Now, one of the most important factor or a parameter which defines the stability of a nucleus, that's what we call as nuclear binding energy. Because see, think about it, a nucleus has protons and neutrons. Protons are positive, neutrons are neutral, basically it doesn't have any charge. And how do we say that the nucleus is stable? We know that even though the entire thing, we have strong nuclear force, that this and all, we have discussed about it. But then the most important factor or the parameter which defines the stability of the nucleus is nuclear binding energy. Okay, let's understand much more about this nuclear binding energy. Now, what exactly do we mean by binding energy? See, binding energy, the energy what is there or energy required to bind to objects, correct? But in nucleus, it works slightly different way. That means when we talk about nuclear binding energy, now we already know that protons and neutrons, whatever, the nucleons in general, they're all very close to each other. Suppose if I have to separate them, okay, how much of energy do I have to give to separate those particles? That is basically nuclear binding energy. Okay, so this is what you are looking at, the nuclear binding energy. Alright, see, remember, it's the work done what we are looking at. That means when you talk about the work done, how much of energy you give this particular nucleus, whatever nucleus you have. That nucleus has nucleons in it. Those nucleons should separate. Okay, and they should separate in such a way that they should never interact with each other. So how much of energy are you giving? That becomes the nuclear binding energy. Alright, to understand about this nuclear binding energy, there is something called as mass defect. In the sense, see, nucleons are held together, isn't it? What is the reason for it? Why are they in that particular place? Why do you think that two protons are attracting each other? Why are they not separating? Because Coulomb's law states otherwise. Correct? Here you are introduced to the new concept called as mass defect. Now mass defect is what? First we take the sum of protons and neutrons separately, and we take the sum of the nucleus. Sum in the sense the atomic mass of the nucleus. Now if you take these two separately and when you measure them, there is going to be change in the mass. Like suppose, let's say, mass of the proton and mass of neutrons, let's say together is, let's say 6 AMU or something. And the nucleus mass is going to be 5.8 AMU. You see the defect? That is what we call as mass defect. Now what happens is that mass defect is there, right? That converts into binding energy. So how much ever mass it's losing, that mass, the lost mass is being converted into energy. And that energy holds the nucleus in one stable condition. Alright? Understood what is mass defect? The change in the mass between the sum of the protons and neutrons and the sum of the nucleus. Sum in the sense the mass of the nucleus. This is what we call as mass defect. Okay, and this mass defect is going to convert into binding energy. Alright, this is the concept of nuclear binding energy. Now mathematically, if you have to calculate how do we calculate the binding energy? Because every nucleus is not the same, so binding energy has to change for every nucleus. Suppose, let's say ZXA, this is an element, as in it's a nucleus, assume. Okay. Now for this one, Z represents the number of protons or basically the charge, correct? A represents the atomic mass. Atomic mass is what? It is the sum of the masses of protons plus neutrons. If I have to calculate what is the mass of the, or total number of neutrons, suppose, let's say, then we take A minus Z. A has both protons and neutrons. Z has only the protons. Subtract, you are going to get the number of neutrons. So A minus Z gives me the number of neutrons. Next, what we'll do, we'll take the mass. Okay, let's say mp is the mass of proton, mn mass of neutron, and m capital N is the mass of the nucleus. Now, to calculate the mass defect, we take delta m is equal to z into mp, because z is what? Number of protons into mass of the proton. Z into mp plus a minus z into mn minus mn. Now, this is the mass defect, the change in the mass, whatever it might be. It could be very, very small or it could be very big, depending on the nucleus. But then, most of the times, generally, the mass defect is a very small value. The mass defect, whatever you're going to calculate, how do we know that this is going to convert into energy? This is where Einstein's equation comes into picture. E is equal to mc square. So what Einstein told, you already know that. That means in this case, E is equal to delta m into c square. Delta m is the mass defect. So that mass defect converts into binding energy. So binding energy is equal to delta m value. Delta m value is what? Z into mp plus a minus z into mn minus mn into c square. Whatever that mass defect we have, that converts into binding energy. In the sense, if you have 0.2 AMU is the mass defect, multiply that by c square. That is going to give you the binding energy of the nucleus. Okay? Now, this is the concept of nuclear binding energy.